Bismillahirrahmanirrahim. In this video we will discuss some examples of the DC machines. So first example that is shown over here, a separately excited DC motor with a constant field current and a constant speed of 3000 rpm consumes 15 kilowatt at the terminal voltage of 125 volt. If armature resistance is 0.02 ohm, we are supposed to determine armature current, back EMF, power developed at the armature or power converted into the mechanical form, and the torque. So the first step to look at this problem is to draw its circuit diagram. So we are given a separately excited DC motor. So here you can see the circuit diagram for that one, a field winding, and over here is the armature winding. Two windings are there and both are connected with the separate supply. The supply for the field winding is Vf and supply for the armature winding is this one, and it is given to us that that armature voltage is 125 volt, that you can see from here. So first of all, draw the circuit diagram, mark all the parameters which are given to you. So armature resistance, that is 0.02 ohm, so that is marked over here, and you can see this inductance over here, but we will not be considering it in the analysis because in the DC the inductor works as the short circuit. So we will not be requiring any information of this inductor part. So we will neglect this inductance in our analysis because this inductor is short circuit. So we will assume that there is no voltage across this inductor. Okay, so now we want to determine the parameters: armature current, back EMF, power developed, and torque. So first step is to draw the equivalent circuit diagram, and next we will start the analysis. So first of all, we are going to determine what's the armature current. So armature current can be determined by looking at the power at this point, and we are given that the machine is consuming 15 kilowatt at the input terminal. So the Pin divided by the armature voltage will give us the armature current, the current that is injected in the machine. So that can be determined as Pin by Va. So 15 kilowatt is the input power and 125 volt is applied at the machine terminal over here. So 120 ampere will be the current that is going to flow in this machine. So the armature current we have determined, that's 120 ampere. Okay, now next step is to look at the back EMF that will be there over here when you are operating this machine under this condition. So first step is to write down the voltage equation, and as you can see over here that this terminal voltage Vt must be equal to the voltage drop across this resistance plus this back EMF. So Vt, IaRa, and the back EMF. So this terminal voltage must be equal to this resistive voltage drop and the back EMF. So if you rearrange this equation, you can write down the equation for the back EMF in your machine, that is Eb over here. So that is equal to Vt minus IaRa, and you know about the terminal voltage, you know about the current, and you know about the armature resistance that is given to you. So plugging in the values, the back EMF is 122.6 volt. So the voltage over here is 122.6 volt and the terminal voltage is 125 volts. So here you can see that terminal voltage is greater than the back EMF. That's why it is going to work as a motor and the power is going to flow into the machine. It will work as a motor, right? Okay, now the power that you are injecting into your machine from here is that we have calculated, that is given to us, that is 15 kilowatt. Out of this, some of the power is going to be lost across this resistance, that will be dissipated in the form of heat. So that is calculated as Ia square into Ra. The rest of the power will be available for conversion into the mechanical form, and we call it the electromagnetic power. And how we can determine that one? The current that is going to flow over here is Ia, and the voltage across this part is the back EMF we are going to assume. So Eb into Ia will give us the power that is converted into the mechanical form. So that you can see the mechanical power that is equal to Eb into Ib, that can be determined now EB is 122.6 volt and IB is 120 ampere. So the power that is converted into mechanical form is 14.7 kilowatt. So out of 15 kilowatt that we injected in this machine over here, the power that is converted into the mechanical form is 14.7 kilowatt. Okay, now we can determine the torque induced over here, the electromagnetic torque, the torque because of the electromagnetic power. So that will be equal to electromagnetic power divided by the speed of your machine, and the speed is given to us in terms of RPM, that you can see over here, 3000 RPM. So this is in radian per second. So the torque can be developed, can be measured by taking or dividing the electromagnetic power with the speed in radian per second. So our power that is converted into the mechanical form is this one, 14.7 into 10 raised power 3, and this is the RPM. So 2 pi by 60 is the conversion factor to convert this 3000 RPM into radian per second. So the resultant torque is 46.82 Newton meter. So what are the steps to calculate this one? The first step is to draw the equivalent circuit diagram, and then in most of the cases you will have to determine the back EMF. Back EMF plays a very important role in the operation of the machine. Whenever you are going to apply the load on the machine, this back EMF is going to adjust itself to a new value such that the new current is established and machine delivers a new required power or operates at the new speed. So with the passage of time during this tutorial, you will see that back EMF plays a very important role in the operation of the machine, and it depends upon, as we have discussed in the theory lecture, that back EMF is equal to K times flux into omega. It depends upon the flux, it depends upon the speed, and can also be written as somewhat like that, KB into IF into omega. It can be controlled by controlling the field current in this circuit, IF, and the speed of the machine. Both are going to affect this back EMF. So we will discuss them more in detail in the upcoming example. Okay, now let's look at the second example. A 110 volt DC shunt motor runs at the speed of 1200 RPM under no load condition, drawing an armature current of 1.25 ampere. So that is the information at the no load. At rated load, the speed drops to 1120 RPM. So determine the input power at no load and the rated load if armature resistance is 0.25 ohm and the field resistance is 57.5 ohm. Okay, so again the first step is to draw the equivalent circuit. So we are supposed to draw the equivalent circuit of the shunt motor. Okay, so shunt motor, your field winding, let's suppose this one is F1 and F2, these are the terminals of the field winding, and these are the terminals of the armature winding. They are connected in parallel. So the machine in which these two are connected in parallel is called the shunt machine or the self-excited machine, and the supply voltage is 110 volt that you are going to apply to this machine. So armature resistance is 0.25 ohm and the field resistance is 57.5 ohm, and we need to determine the input power at no load and the rated load condition. So once you apply this supply to this machine, the voltage across your armature and the voltage across your field both will be same because they are in parallel, and that will be equal to the terminal voltage. And as we have already discussed, this inductance LF is not going to play any role, no voltage drop across it. So we will simply calculate the current in this field winding by dividing this terminal voltage, that is the voltage across this winding, by the resistance of this branch, and that is 57.5 ohm. So that you can see VT over RF. So 110 volt is you are going to apply 57.5 ohm. So current in the field winding will be 1.913 ampere. That's the current in this. Okay, now it's a shunt machine, so this supply current, that is IS, that will be the sum of this armature current and the field current over here. So you can write down the equation that IS is equal to IF plus IA. So the field current is 1.913 ampere, and the armature current is given to you that at no load your machine is taking only 1.25 ampere. So the field current 1.913 ampere and the armature current 1.25 ampere. So the total current that will be drawn by your machine at the no load state is 3.163 ampere. So this current is 3.163 ampere that is being drawn from the source, which is at 110 volt. Okay, now what's the no load power? No load power can be easily calculated by looking at the input current and the input voltage, the applied voltage, because you know that the power is equal to the product of the voltage and the current. So the voltage that you are going to apply is 110 volt, and the current in the machine from this supply is 3.163 ampere. So the power that is injected into this machine, that is equal to 347.9 watt, the power taken by this machine. And please note that this is at the no load state. We have still not applied any load, mechanical load over the shaft of this machine. It is rotating with speed omega. The induced torque is in this direction. When you will apply the load torque, so that will be acting in the opposite direction to the induced torque. So at the moment, without the load torque, what is the power that is being drawn? That is 347.9 watt. Some of the power, this power is basically required to run the machine itself, to overcome its own inertia, its own losses. So this is the power required at the no load. Okay, now let's look at the back EMF at the no load state, because when you will apply the load, your terminal voltages are to be kept constant. This one is to be kept constant. So this back EMF must change so that the current that is injected into the machine is updated and the torque induced is updated, because you know that from theory class the torque induced is equal to KTIA into IF. So the change of current will bring the change in the torque. So as our field is connected across the constant voltage, so it is going, the field current is going to remain constant. The armature current will change as the load will change, because more induced torque will be required, right? And that armature current can only change in this loop if your back EMF is going to reduce. So now let's look at it, what will be the back EMF at the no load state. So the back EMF is terminal voltage minus IARA, neglecting the voltage drop over here, no change over here. The voltage drop over here will be only effective during the transitions, during the change of the current. So at the moment I am going to assume that the constant current is going to flow, and this part is not participating in any voltage drop over here. Okay, so now if we plug in the values, and so you can see 110 volt armature current is 1.25 ampere that is given to us, and the armature resistance is 0.25 ohm. So the back EMF at this point is 109.7 volt. So this back EMF is 109.7 volt under the no load conditions. Okay, now let's calculate the power that is converted into the mechanical form under the no load state. As there is no load, so this power is not for the load but for the machine itself. Machine has the weight, the armature has the weight, it has the inertia. So some power is required to run that machine itself. So that will be equal to this voltage EB and the current in this branch, and the current in this branch that you can see over here is IA, the armature current at the no load. So the product of these two will give you the power 109.7 volt into 1.25, so 137.1 watt is the power that is required by the machine to run itself. Okay, as I told you earlier that once you are going to change the load, the back EMF is going to change, because if it is not going to change, the current cannot be changed over here. So to change the current in the armature, this back EMF must change, and as we will be increasing the load on that on the machine, so that requires the increase of the current, so this back EMF will be going down. So the back EMF, as we have already discussed in the theory class, that is proportional to the flux and the speed. So at no load the back EMF will be given by this expression. It can be written in terms of the field current, because flux is proportional to the field current, and this is the speed in radian per second, and this is the speed in RPM. So by a constant factor we can convert from radian per second to the RPM. So that is accommodated in this one, some constant in the new constant. So constant into constant, it will be a new constant. So I have represented it with K1. So this equation can be written as K1 IF into NL, no load speed, that is in the RPM. So similarly, if we consider the full load, so at full load your back EMF can be represented like that: K flux at full load, speed at full load. So this can be written as K1 IF speed at full load. So if we take the ratio of these two equations that is shown over here, that EBNL over EBFL, that will be simply equal to no load speed divided by the full load speed. So if you know the information of this equation, that is, you know about the no load back EMF, and you know about the no load speed of your machine, and if you calculate and you know the full load speed or any three parameters which are known, you can find out the fourth one. So we are basically interested in calculating the back EMF at the full loads, and that will be given by this expression, that this ratio of the speeds full load and the no load into the back EMF at the no load. So we have calculated the back EMF at the no load, that is 109.7 volt. And what is the speed? The speed that is given to us over here. Here you can see the no load speed is 1200 RPM and the full load speed is 1120 RPM. Right. So using these values over here, that 1120 is the full load speed and the no load speed is 1200 RPM. So your new induced back EMF will be 102.4 volt. So the back EMF over here in this circuit is going to reduce this back EMF. At no load it was 109.7 volt. At full load it is 102.4 volt. Terminal voltage is 110 volt. So the current in this branch will be changing because of the reduction in the back EMF over here, right? Okay, now what will be the change in the current, that you can determine with the help of the generator equation. You know that the terminal voltage is equal to IARA plus back EMF. So now you know the back EMF at the full load, so you can find out the full load armature current, that is equal to VT minus back EMF at full load divided by RA, the armature resistance. So just plug in the value. This is the voltage, this is the back EMF at the full load, armature resistance. So 30.4 ampere is the full load current of the armature. So the armature current has changed from 1.25 ampere to 30.4 ampere at the voltage of 110 volt, right? So by applying the load, the armature current increases, and how it is going to increase, that your back EMF is going to decrease, that was basically opposing the current in the armature. So you can observe the increase in the armature current over here. Now you can work out the full load power, the power converted into the mechanical form, that will be equal to this back EMF multiplied by the current in this IA, that is the full load armature current. So here you can see that mechanical power is EB into armature current full load. So 1024 volt that we calculated over here, and 30.4 ampere. So the new power is 3110 watt, that is 3.110 kilowatt. So for kilowatt you will have to divide it by the 1000. So if you divide it by the 1000, you are going to get this factor, and you can represent this power in the kilowatt. Okay, now what will be the new supply current? The supply current over here, the field current has not changed because field resistance is fixed, and the voltage across it is also fixed, 110 volts. So there is no change in the field current. Armature current has changed. So the sum of these two current, because the supply current is equal to the field current plus the armature current, so that you can determine over here, that field current, that is 1.913 ampere, and the new armature current is 30.4. So your new supply current will be 32.31 ampere, that will be drawn from the source, right? So this is the new current over here. And now what will be the total input power on from the source at the full load condition? So the voltage is 110, and the new supply current, that is over here, is 32.31 ampere. So taking the product of these two, so the new input power is 3.55 kilowatt. So when you increase the load on your machine to the required level, so it is now going to draw 3.55 kilowatt from the source terminals. And if you go back and look at over there, under no load state it was only drawing 347.9 watt. So with the application of the load, the input power to the machine has increased, it has adjusted its back EMF, and the armature current is set to a new value and supply current is set to a new value, and machine is going to provide you the required speed and the torque induced for the load, and the load torque is going to act in the opposite direction. A mechanical load is considered to be connected over here. So that's all from this video. In the next tutorial we will discuss about more in-depth analysis examples for the DC machines. Thank you very much.